share my screen. You see my screen? Can you see my screen?
Not yet.
Not yet.
Okay. I'm going to have to escape here. Let's try this. Better?
Yeah.
Okay. Thank you for the invitation to this this conference. I was asked by Dr. Mel Lewis to speak on irrigation. And one thing I've learned from this conference and from working with colleagues is that the management of turfgrass is a kind of integrated, holistic thing, and it's not about one area. So when I talk about irrigation water management, it is not isolated from the other things that our guests have been talking about, including turf pathology and insect management and drainage and all the other things that have been given at this conference. So I'm going to try to focus on irrigation, and it's going to be a mix of sports fields and homeowner, light industrial, commercial irrigation, which is different in terms of the equipment, but not in really the physics or anything else that we talk about from a kind of a general theoretical concept. So I'm going to try to play this, and hopefully you can, do you see my slides on the side? Do you see my whole screen? I'm going to go ahead and see if I can play from the start and see if that works. And it may not, but we'll try. Okay, do you see my screen still?
Yes, full screen.
Okay. So first I wanted to start with performance evaluation of turfgrass irrigation systems. And what I want to talk about here is in order for you to manage your irrigation, it's essential to know your system. And so through this talk, I'm going to give you some background on how what parameters we use to measure irrigation systems and how that we can do an irrigation system audit and look at manufacturers' charts and use everything in our knowledge to try to characterize that system so that when we go to manage irrigation, we can program controllers correctly, we can hit a target closely, and then adjust from there. So I'm going to focus on that. So this is going to be looking at performance of the system itself, and then we'll talk about irrigation water management in the next talk. So when we talk about this, I'm going to list a couple of objectives. There's really a number of objectives, but two in particular, we're going to come away with numbers. One way to get to performance evaluation is simply by using manufacturers' charts. Rainbird, Toro, all the big players have manufacturers' charts that are specific to their sprinklers, whether they're rotors or whatever types, that tell you the performance given a pressure, how they will perform in terms of flow rate and distance of throw and those sorts of things. But we also want to look at how do we calculate a precipitation rate. And here, in the agricultural background that I'm from, we like to talk about application rates and associate those with the irrigation system versus precipitation rates, which we think of falling from the sky. But just know that if I say precipitation or application rate in this talk, I'm talking about the same thing. That's the rate at which the system applies water, usually in length per time or millimeters per hour. So about uniformity measures, how do we calculate them, what they mean, what kind of ranges we're looking for, and then we'll end up with going through how do you perform an audit, give you an example, and then end up with a couple of resources that may be of interest to you. Okay, one of the main objectives in evaluating system performance is determining the system's application rate. And while there are many other objectives, if you do not know this, it's going to be difficult to program run times in your controller, or even if you manually water, how long to run the system to achieve the desired depth of application you want. So that's of importance. Here you see in the left panel, a student worker for an irrigation audit we did in a local town And those are just catch cans that we're collecting the depth of water, and we can determine how uniform and what the application rate is by doing that. This is a very old publication, but it's very good. It was done in the 40s at the University of California, and it's an extension publication on irrigation by sprinkling. If you look at the left here, if I can control my pen over here, maybe not. So here is overhead or bird's eye view of the distribution of water of a sprinkler. And you can see here in this middle, it's pretty high application. It corresponds to this cross-sectional view. And then there's very little applied out in the middle, which corresponds to this area. And then on the edge, you see you get a higher application rate or depth, either way. And then this is in the other direction, but you see the same thing. And we would call this somewhat affectionately a donut pattern. And it's very typical of something with low pressure. So this is 20 pounds per square inch, which is equivalent to 1.4 bars or 140 kilopascals. And that's what you might see under a low pressure condition. This author categorized sprinkler distribution from a single sprinkler into these classical patterns. You see A, B, C, D, E, F, and they're really normalized and simplified to meet like a triangular or kind of a parabolic shape, or this type of a shape, and even the worst, this kind of a donut pattern. So this was research that was done many years ago, but I think it's the point I want to make here is that one sprinkler will not apply a uniform pattern by itself, and that's why we need to overlap. Now, different overlap or the space of the sprinkler is different by the type of sprinkler. If you overlap more, you may be more uniform, but you also are going to pay for it because you're having more hardware. So I'm going to switch back here. Okay, so I'm going to divide this into either sports fields. Here on the left, you see a golf fairway with large rotors irrigating, and that in homeowner or light commercial industrial type of applications. Here, these are also rotors, same general type of sprinkler here, but a smaller radius, smaller discharge. Here again, this was an audit that we did locally in a study. So they're similar in concept, but we're going to have some difference in details. I did a little research. I'm not an expert in golf course irrigation, but I went out and looked at some things that are available now in terms of nozzles for golf course. These are Rainbird rotors, and you can see all the different nozzle configurations. So you can see quite quickly that it became rather complicated in selecting the appropriate nozzle and configuration. This is a very simple nozzle. It just has one nozzle like you would see in the landscape application with what we call a nose spreader. And you'll see that in the next slide, what I mean by a spreader nozzle. This is a spreader nozzle here. You see the primary nozzle and a smaller nozzle. The smaller nozzle or a spreader nozzle is meant to irrigate in a closer radius or throw from the turret here, the pop-up rotor, so that you just don't throw a lot at distance and not get anything around the head. Here you see something called a cascade nozzle, and I think the cascade is because of this X pattern. It will actually throw a sheet of water. And finally, over here, there's a dual spreader. We have a spreader nozzle on either side of the main nozzle. So when you're selecting golf course nozzles or doing an audit or looking at them to find the correct chart, it's going to be a little bit tricky to make sure you get the right chart. Now, a lot of these nozzles and names are a bit of marketing, I would say, and it doesn't mean they're going to be better, but they're different configurations. So when I talked about the spreader nozzle, you can see right here in this gray area, that is the area covered by the spreader nozzle. And this one has a rear nozzle, like the old agricultural sprinklers. You'd have the main nozzle one direction, the spreader pointing 180 degrees in the other direction. And then this is for the main nozzle. So that gives you an idea of the coverage from a bird's eye view. What we want to look at here in terms of reading the chart is that you will enter the correct series body for in this case, a rotor. You will go to the correct color-coded nozzle, and they color-coded the nozzle, and we'll see that this is also a number 28. Well, a number 28, if historically and by convention, would be in 64ths of an inch, at least in the agricultural world. And I think that applies here. I'm not exactly certain. The problem in the irrigation industry is nothing is totally standardized. So you have to be very careful about interpreting numbers. But in any event, they show you by the color code that at a given pressure for a certain nozzle, as we increase the pressure, you see the flow rate increase here. The flow is going to increase with increased pressure. There's no surprise there. It's usually as a square root of the pressure. And then as you get a larger orifice, a bigger nozzle, you'll see the flow increase too, up to a certain point. And then you see here with the diffuser, that means we're actually breaking the spray up, and that's actually probably impeding some of the flow, and that's why you see a lower flow rate. But for any of these pressures, and if I got this right, this is actually 4.1 bars at 60 pressure, 60 and 70 and 80. Move back here. It would be 60, 70 and 80 PSI, and these are bars for metric. I tried to present metric for the group. So some of these rotors, which most oftentimes contain their own solenoid valve within the sprinkler, so each can be controlled individually. You may be able to get preset pressure regulation, and that is advantageous so that you have a known pressure, and so you could go to the chart and be confident that the discharge is correct. And then you can also adjust. So these are color-coded and you can adjust the pressure, but if you adjust the pressure, you may not exactly know where you're at, but we can see there's ways to measure pressure a little later on in this presentation, I believe. So pressure regulation, it prevents overpressurization. It will not increase pressure. You're only knocking it down if you have excess pressure. And that can be good to prevent too much sprinkler breakup of the stream and creating very small droplet sizes. Very small droplet sizes creates drift and goes off target, and it's subject to more evaporation. So you can only reduce pressure with pressure regulation from the supplied pressure. You can't increase it above the supplied pressure, which we think was obvious, but some people probably don't understand that. Okay. So here's another example of a nozzle, and here they have LA here, where my arrow is, means low angle. So another configuration, or another category of how we characterize a nozzle could be the angle of the stream. And if I might be able to, so a lower angle would have maybe a stream like this, and a normal angle would be higher. And the reason you might want to choose a lower angle is to fight a windy condition. Of course, with a lower angle, as you'll see on here, you have less of a radius. So it goes from 8.8 here at the number 18 nozzle at 4.1 bars, from 8.8 to 5.8 meters of radius throw. And that's because it's just thrown at a lower angle. it's sort of like hitting a golf ball or something like that. If you get the right arc, it's going to go farther. So anyway, select the correct nozzle category or color or size, and then you can read the radius of throw and the flow rate. Here is in liters per second or meters cubed per hour, based upon the pressure. And this is in bars here, 3.4 bars, or about 50 pounds per square inch in English units. So, we'll talk about golf course are pretty high pressure systems in terms of what you want to supply to the rotors. Okay, so going to landscape irrigation, you'll see this is a rotor just like a golf course, but it's much smaller. And this, I think, is a 6-inch stem that pops up. And you can get them in different stem heights, different body heights, and that's for clearance. So if you have maybe a 4-inch stem or a couple centimeters, then it may not clear some of the taller turfs like tall fescue. So you have to make sure you select the correct the body size for pop-up. Our rotors, which actually pop up too. Some of these are spray heads, and they just spray around anywhere from a quarter circle to a full circle. The purple you see here is indicative of a standard for wastewater irrigation or reclaimed water. Now, these are no different hydraulically than normal sprinklers. However, they will slap the purple cap on them and probably charge you more. They may be a little more robust in terms of corrosion, but really the same type of sprinkler. Special features you can get with even landscape sprinklers now for homes is pressure regulations and check valves, such that if you turn the water off, it doesn't all flow out of the head. It will check it out. But again, we'll look at application rates and discharge and radius, and that from a manufacturer's chart, and we'll get to uniformity a little bit later. So what do we talk about in terms of precipitation rates? Precipitation rate or application rate is going to depend on not just on the sprinkler, but in the spacing, how close or far away you space them. The closer you space the same group in the sprinklers, the higher the application rate, because you're putting out more volume of water per unit area, per unit time. But the fixed spray heads, and you might have seen them, tend to get really misty. They generally have the highest precipitation rate, anywhere from 25 to 100 millimeters per hour. So you have to be careful with those in terms of watching for runoff and over application. Rotors and the other typical landscape sprinkler is lower in application rate, generally at the appropriate spacing, 5 to 50 millimeters per hour. There's kind of the in-between, not really in between, but something called a multi-stream rotor that was introduced several years ago. And that's a lower application rate than the sprays because it's really covering a greater distance, and assuming you're spacing them likewise. So with a high precipitation rate, you may need to what we call cycle and soak, or split the application and run it for 10, 15 minutes, stop, wait 20 minutes, run it again, so that the infiltration rate is not exceeded with the soil. And the soil infiltration rate usually starts high and then ends up at a basic rate, something like this over time. If we had rate on this over here, can't write very well with this cursor, with this mouse, but in time, ultimately it's going to get to what we call a basic infiltration rate to the right, where it levels out in that curve. And you don't want to see, application rate should never exceed that, because it's not going to go in the ground, it's going to run off. Okay, here's an illustration of a landscape rotor. This is called a T5. Toro is the manufacturer here. So with a given nozzle size, and here's a nozzle size here, and really the three here that you can see me circulating with the arrow, is the nominal gallons per minute expected of that nozzle at the pressure given in bars here. So from that, I've circled this one thing. So one row here for this nozzle, which is what we call in the US a 3 gallon per minute nozzle because it has 3. At 3 bars of pressure, which is about 45 pounds, I think, per square inch, it's going to have a radius of 12.1 meters and a flow rate of 0.68 cubic meters per hour. So that's a fairly high flow rate. I think liters per minute, 11.3. No, that's not, it's probably about, okay, it should be about 3 gallons per minute. Now you see the precipitation rate. How do you interpret that? Well, the assumption on these manufacturers' chart is that you are spacing the sprinkler at the radius provided, radius given. If you are not have your sprinkler spaced at this radius, or what we call head-to-head coverage, it will not have this precipitation rate. Now note in this chart also assumes that you have a 180-degree arc. So for these rotors that you could set for different arcs in the horizontal, this would be an 180-degree arc. That's the assumption in this table, is that you are setting the horizontal arc, and when it goes back and forth, at 180 degrees and not 360. Because if you do 360, you will get a different application rate. You'll get half that application rate. So if you were to have a full circle configuration, it would be half of the application rate this chart. So I went through the calculation and saw it was wrong, and then I figured out why. So be careful in interpretation. And sometimes they don't tell you this. Hopefully they do, at least in the footnote. The other thing to note that this is a square here. That's for a square spacing. And this is for a triangular spacing. And we'll look at that shortly. So here's another a spray head. A variety of angles that you cannot set these, you buy them with that angle. And that is the angle of discharge for a spray head in some of these landscape systems. So anything from 60 degrees to 360. The 5 here in the mole number is the nominal radius. And again, the precipitation rate assumes a sprinkler spacing of the table radius at the given pressure. So they'll look, they give you a precipitation rate here. It's based upon that flow rate and that radius in the table. So usually when you get these small landscape homeowner type things, they only range to maybe not much more than 15 feet or 4.5 meters in throw of radius. So how do we calculate a precipitation rate? Well, here we have the square spacing here where this S equals that S, and it's nice and square. We're looking at what's being thrown on between 4 sprinklers here. And in SI, simply liters per minute times 60 to get it liters per hour, divided by your spacing in meters by spacing in meters, and that will give you millimeters per hour. In US customary or English units, where you have this very strange looking 96.3 units conversion times gallons per minute times divided by the this dimension by this dimension, or S squared in this case. If we look at a triangular spacing that we see, we'll see that it's triangular spacing. This S is a little bit further apart or longer or stretched than this L. So what happens in the triangular spacing is, I think it should produce something that's, because S is longer here. Now this is S and this is L, because L is shorter than this S. This S equals that S, excuse me. You actually get a higher precipitation rate in the triangular configuration. You're looking at you're looking at what's being thrown between these three sprinklers in that configuration. Or if you want to look at it another way, it's kind of a stretched parallelograms. You're getting a little bit more area in here for the same sprinklers that you had over here. So just some subtle differences. Supposedly the triangle pattern produces a better uniformity. I am not, I don't get hung up on triangular versus square. Use whatever you want, it's convenient. The multi-stream rotor I showed before looks like this, and it just actually swirls around. It's kind of fun to watch, but you don't see too many of these. And this is some a testing unit that they tested it on, and they argue that it gets a better uniformity than spray heads. Note on this graph, there's something called the scheduling coefficient. Never use that because you are trying to satisfy the lowest or the driest 5% of the land that you cover with these sprinklers. And to do that, you have to triple the runtime. You don't want to do that. That just becomes not wise at all. We'll talk about really how to cap a runtime, even if you have non-uniformity issues, because you just don't want to over-irrigate some places. Okay, what about pressure regulated heads? They can be good, and we looked at them in the golf course setting. They're built-in pressure regulation. You can get those in landscape sprinklers too, especially for the pop-up spray heads, because they typically have a lot of misting and fogging under high pressure. So you'll go prevent that by regulating the pressure or cutting it down within the body. It's actually in the stem on the fixed sprays in landscape systems, and typically rated to the 30 or 40 PSI, or about 2 to 3 bars of pressure. So no matter what comes in, that's nominally maybe 10 PSI, a little bit higher than the regulated pressure. It will not increase in pressure. And we'll take a look at that a little later, next slide or two. So essentially, if you have, usually if you have an inlet pressure in the body, it's gonna, the outlet pressure is gonna increase with what's coming in, because it's just going through this mechanism and out. And you're gonna get the pressure at the outlet and commensurate flow increase and spray breakup, which you don't want with a normal head. But if we regulate, and we actually did a study on this at NC State, we actually took some manual heads, took the nozzle off, inserted a T adapter, measured the inlet pressure, the outlet pressure, and recorded that so that we could set up a test that others could follow to evaluate these spray heads that come on the market. As you might know, these spray heads come out with various claims, and some people really want to know how they perform. So we did this way back in 2012, and the reason we did it was just to set up a protocol by which we could hand this over to a third party and have them test it in a reasonable fashion. We actually didn't come out with a report. We just came out with a protocol. So here you see what we had set up. These are pop-up spray heads out behind our building. And we hooked all these water meter, pressure meters to a Campbell Scientific data logger and logged the data, and then made our evaluation given various inlet pressures, what the outlet pressure was, and if it in fact regulated to the advertised pressure. The side benefit of this is you could run your car up here and get a car wash. Not really, I'm just kidding here. Okay, so let's look at a couple of results. This is a Rainbird, and I can divulge this now because it's not top secret. Rainbird pressure regulating spray head, 4-inch body, a 180 spray. That means it's half circle spray at 60 pounds per square inch, or about 4 bars of inlet pressure, as you see right here. We measure the outlet pressure, and the advertised regulated pressure is a straight line. You can see it's right on. there's little fluctuations with the supply pressure and whatnot, but it did excellent. Next, we wanted to jack it up and see what would happen. So we raised the pressure clear up to 100 PSI, or about 6.9 bars. Here's our inlet pressure over time, and our outlet pressure. Here's the target. It is a little bit off, but not by too much. Amy is at 32 to 35 pounds per square inch. So it still did a quite good job, even when we increased the pressure to very high pressure, something you would not get at a home normally from a service line, but just to test it, and did quite well. Now, I will say that not all brands did well. In fact, some did poor, and I don't remember which ones they were, and I won't mention them anyway, but this was Rainbird, a good standard brand. I'm not here to promote any brand, but Rainbird and Toro are probably the two brands you would hear worldwide most often. Okay, let's go into how we do a formal audit of a system. Now that we've looked at some of the ways that we measure performance of an individual sprinkler, how does the whole system perform overall when we lay out sprinklers, install sprinklers, have certain spacings? But why do we do this? Life is not simple, as most of us know. It's a little bit messy, so we don't have perfect squares, perfect triangles. And the charts, are helpful when we go to design a system, but in reality, we want to go on the ground and field test. We might not know the nozzle pressure. There might be an irregular sprinkler spacing. Additionally, we want to monitor the conditions that may be native to the soil's slope and look at runoff, because it's not just about run times, it's do we incur runoff at certain run times of irrigation. So we'll take a field measurement of the application or precipitation rate. And then from that, we can do a uniformity assessment. How uniformly is the water being applied over our irrigated area? Also want to look at potential runoff. So ultimately, we're looking at how we're going to program our run times and cycles. Now we'll stop here and make sure you know that there's a number of cultural reasons or operational reasons that you're going to program irrigations at certain times. And that's because you have traffic or you have sports events, and that all should be taken into consideration. Okay, objectives of the audit. It may end up in reducing your water application, but that's no guarantee. What we're really after is trying to put on the right amount at the right time and have a reasonable uniformity. You also want to obviously improve your landscape appearance. You definitely want to reduce your irrigation water runoff, and we can control that with some cycle and soak, or even re-nozzling and putting on less water out from each individual sprinkler. That works. We don't want any water loss that goes down below the root zone. We call that deep percolation. And if our run times are too long, it's either going to run off or go to deep percolation and not be stored in the soil. So basically, though, it's going to aid in our irrigation scheduling and control our programming. And that's through measurement of application rate and application uniformity. Okay, these slides, next slides, are courtesy of Dr. Miller, who spoke earlier, who did a lot of talks and pictures of sports fields. Actually, this is one that I saw him show. I always say, trust your eyes. Observation is a wonderful thing. Don't just crank numbers and put them in a controller. Always look and get field truthing. Well, to me, this is pretty obvious that either it was insufficient pressure and that didn't throw far enough, or the designer put the sprinklers too far apart, or incorrect nozzles, or any combination of that. That, believe it or not, is not too unknown. I've seen a number of wastewater irrigation systems where they just want the circles touching. That is not what we want. We want them to be overlapped. Here, another one that Dr. Miller showed, overwatering. You can see the tread marks of the vehicle. that went over for mowing or whatever, and you can see this leaving marks, it's too wet. No, over irrigation is not good for a number of reasons. It's also promotes disease. Drainage. So all the things when you're doing an audit, and even when you're operating the system during the audit or afterwards, you want to look for things on the ground that tell you you're putting on too much water, or your drainage is not, your field isn't correctly graded, or you have drainage issues. And I think all of us have seen something like this. This is obvious, but until you go out there and watch the system operate, you may not know that happened. Unless you look at your water bill and you're paying a water bill and not pumping it from a lake, you will get a surprise when you look at your water bill because you've used a lot more water. And so that's equipment damage. You want to make sure your equipment's in good running order by visually observing it. Okay, what do we need if we're going to go perform an audit? Here's kind of a laundry list. Primarily, we need something to catch the water in. These are catch containers or catch cups. It's important you have the same entrance, or the top of the cup is the same diameter, so that when we can measure a volume and we're okay. You don't want to have cups of one size and cups of another size and then go measure the volume of water. It's not going to be correct. A graduated cylinder, we use that to measure a volume, and we convert that to depth by knowing the surface area of the cup. You want some way to time your application so you know your rate. Flags to mark your heads and your zones if you want to isolate zones for auditing. You may want to get a pressure gauge, and we'll look at the pitot tube next, and all these other things that are just general good tools. So I say I laid a few of these out in my garage the other day. If they're not complete, here's flags, clipboard, right, record your results. And here's just an example of audit. Now these are all lined up in a nice row. Unless you want to do a spatial analysis on a graph and see where exactly it's non-uniform, which is good, you don't necessarily have to do that. You can randomly set the cans. And even if it's random, I guess you could plot it out where it's located, but it's easier to plot it spatially if you want to get an idea of spatial distribution and not just a number of uniformity. But you're going to need a whole lot of cans. You can buy cheap ones. Dr. Miller got these at Florida when he's at the University of Florida, and they were just the cups that were provided at the stadium for football games. They were very cheap. And we used a nominal 3-inch PVC to set those in, so you have something that will keep them upright and weighted down. Okay, so before you run the audit, you want to record the existing controller settings. You want to flag all the sprinklers, and you want to know which zone is contributing to what area. You're going to run zone at a time normally. And you'll note the sprinkler type, record the pressure if you can. You want to adjust the sprinklers for the alignment and arc such that you don't evaluate a sprinkler that's way out of alignment to start with. You want to start with what you can expect of that system. And a diffuser screw is just a little screw that you screw down into the stream to break up the stream, and to actually reduce the throw the further you screw in the screw into the nozzle. Nothing beats walking around taking drawings and photographs. Here's one now. This is my drawing. It's not exactly a Leonardo da Vinci prize drawing, but at least I can read it, and it shows the different zones I've numbered here. Shows where the valves are. And in this case, it shows where we're going to install a sensor-based smart system, and so we can attach it to the zone. You will see in that homeowner systems, if you have the opportunity to see them, are all over the board in terms of the quality of installation. We've seen many installations that are poorly done. Here you see the line coming out of one of these zones that is laying on the ground. So even though we have certified irrigation contractor licensing here. There's still some shady characters out there are not very professional and will not install it correctly. Here you have a slope, so that's going to be a problem with runoff. It's going right back to the lake, and in this case, they pump it to the lake, to the irrigation system, and if you overwater, it's going right back to the lake. Here's another illustration of poorly installed system. You see a couple of zone lines that are been eroded by this driveway, and you can see them. Okay, how do you might take a pressure measurement? Here's, you can take off on the spray head, take out the spray head here, insert the adapter, hook at the pressure gauge, run it, and you can see the pressure on a regular pressure gauge here. Another way to take pressure can be to hook what this unit here is called a pitot tube. Next time you get on the airplane, if you've been on airplanes before, you'll see them coming out the side, and that is to judge velocity or to give the idea of velocity. It converts what we call a velocity head to a pressure head, and it registers on here. If you have a good sized rotor stream, you can do it. You cannot deal with spray heads because you don't have a good stream to put that into. That's another way to measure pressure. And then you can look at your charts and get an idea of flow rate. Okay, so here's another just example of a house we did an audit of and laying out the catch cans. We generally would take a different color flag, have a common color per zone, and then use a different color flag for a different zone. There's no set rule in the spacing, 2 meters is usually sufficient. You want to have a number of cans between the sprinklers and this complete your array. On golf courses, you can space it out a bit more because you can get into hundreds of cans on a golf course if you're doing a fairway. Here is an example of just observing the system while you're doing an audit. And I can tell you right here that this system has pressure in terms of pressure. It's low pressure, so you see a stream here that's not well distributed. It's just a stream. And you can see all the water's coming out here, and there's very little in here. Most light commercial, industrial, homeowner systems, if they tend to be one way, they tend to be under pressurized, which means they're running too many zones on one, too many heads, on one zone, or your pump is insufficient, not generating enough pressure. If you're getting it from a service meter from a city, there's only so much you can do, and there's charts for those in terms of the diameter of the service line and what pressure and flow you can expect. So it's important to know what's coming into the system, your pumping system, or what you're getting from the city and municipality before you put too many heads in a zone. Okay, so here's just a kind of a color graph of these are application depths, I think in inches in this case. And this is a very good system. This coefficient uniformity was 84. That's quite high. Distribution uniformity of 70 is quite high. That's more than we normally see in a homeowner situation. Obviously, the more these numbers are close together, the better uniformity. So the other thing you have to watch out for is you put catch cans on, and if the stream of water is a low angle and it bangs up against the can, it doesn't fall vertically in the can like rainfall does, you might see a much lower catch rate in the cans than you would if you looked at what went through the water meter divided by the area and divided by the unit time you applied it and get its rates. In this case, it was about 50% higher measured through the meter than we caught in the cans. So that's just another thing to be watchful of. The height of the can versus the height of the stream and how it's falling can affect your measured precipitation rate. Okay, just some general ways to measure water here. We have application rate is simply, take our average catch depth over runtime, that's length per time, and we want to divide that by 60 to get to hours in millimeters per hour. This is the equation. And we can rearrange the equation to get our average catch depth. If we know our rate, we can set our runtime based upon this equation. And so we can have a target depth and we know our rate. We can rearrange this equation, bring this down over here and get a runtime. They're all interchangeable. So here's actually a calculation. Now we're talking about how do you actually calculate these standard uniformity measures. DU, low quarter, or if you don't see the LQ, is just DU. That's the average catch of the lowest quarter of catches divided by the overall average. That's a pretty stringent measure, and it's going to be a lower number than what we call the distribution uniformity of the lower half, which is the average of the lowest half. We rank them here. You can see in the spreadsheet I ranked them here. This low half divided by the overall average. That's going to be a higher number than that. CU is based on the average absolute deviation from the mean, and that normally is pretty close to the DU low half. You can actually get a CU negative because if you have the absolute average deviation is greater than the overall average, you'll get a negative number. And I've done that before in a wastewater irrigation application where the sprinkler stopped rotating and it put a bunch in some cans and not very much in other cans. Here's a plot of a green. I think Dr. Miller supplied this one. So if you can spatially represent what was caught, you can see that there's some very dry spots on the edges here and relative wet spots. So this gives you a nice color image of what I do not know what these units are in this key, but it's just relative. You can see that uniformity may not be very good on this green, in which case you have to do hand watering or syringing or whatever you need to do in the dry spots such that it wouldn't be too dry. Here is an example of an audit I recently did. It's actually at our church, and there's one irrigated section. So I thought it'd be kind of interesting to go out there and look at the application, uniformity and rate. You can see here's a bird's eye view or plan view of all the catch volumes, I believe, in this case. And you can see how they were laid out here. This was a poorly designed system. There's one zone has one sprinkler here. The other zone has 1, 2, 3 sprinklers, which you should not do. You should balance your sprinklers per zone. It's based on the city water supply. You can see there's hot spots here. Now, if I were to design it, I would have put the sprinklers on the edge of this elliptical area and thrown them toward the middle. Here they didn't, so you have problems trying to adequately irrigate the edge. And so it's not a very well designed system. And consequently, our DU low half is not terrible, but it's not great. And you can see in this case, as I mentioned earlier, it's equal to the coefficient of uniformity. Those two measures are usually pretty equal. And the DU, which is low quarter, is not very good. So we were to look at a distribution graph here. Here's our target depth, or in this case, just our average applied. And this is in inches. And you can see that there's some here that just a few that have very high rate. Well, quite a bit in the middle here. And that's where you see this really high hot spot. And this is actually after I went and re-nozzled some of these down, because the first audit, I saw runoff after 15 minutes. So I went in and reduced the nozzles, I re-nozzled. The uniformity did not improve, it actually went down a little bit, but I think the runoff problem is a little better. Some resources for you, if you like. You just Google landscape irrigation auditing made simple. It's an extension publication from NC State done by my colleagues. I think I contributed a little bit, but not primarily. Dr. Miller, and then Dr. Drew Penix, who's recently graduated, graduate student of Dr. Miller. And on that, it has more links here to get to that. So if you just Google this, landscape irrigation auditing made simple, you should come up with that publication. You can download and take a look at it. It gets into more details about the audit itself. And if you're a user of R, it may be more for the university types. R is freeware. it's statistics and many other things, graphing and a whole array of things you can do with it. I wrote a package for that called SPR EVAL or Sprinkler Evaluation. And you can download that from the CRAN site or from my GitHub site here. And it's really more geared for agricultural irrigation, but you can use it if you're doing some of the functions in there that I have can be used just as well for landscape or golf course irrigation. Anyway, that's just for your FYI. I can be contacted at this email address down here, glgrabow@ncsu.edu, and I'd be glad to answer your questions. I'm emeritus professor, so I'm retired, been retired for about 3 years, so I can't guarantee I'll get back to you really soon, but I will try to answer questions if you shoot me an email.
Hey, Gary, I'm your official translator.
Okay.
There is a question in the chat. I've seen that in soccer fields, they don't necessarily use filters, which makes the rotors get obstructed.
Right.
Can you, in your experience, can you comment about filters? What are the most used ones?
Yes. My experience comes from more agricultural applications, but there are an array of filters. You can get screen filters that are used a lot with groundwater if you have a sandy stratum you're pumping from. They're disc filters that actually are a stack of discs on a spine that the water has to pass through, and that takes the sediment out. And then after it gets a certain differential pressure across those filters, it will automatically pop the spine up, expand the disc, and backflush the disc. So there's also just screen filters and disc filters are the two major types. And usually it's more of an issue of drip irrigation. If you have large nozzles, you usually don't have this problem. So I've not really seen it too much in something like golf course irrigation, but I could see that if you had a lot of sediment in there, and then it might cause issues. But so screen filters and disc filters are the two general types, and you have to size those correctly for a certain flow rate so that you don't overextend them. They have enough capacity, and those will be rated in gallons per minute per square foot of screen or disc area. There's different screen sizes, different disc sizes in microns, and screen sizes and mesh sizes. So you have to, they're all a little different, but there's a variety of screens and filters you can use. Okay, so it looks like we're.
I have a question for you. What do you think, in your experience, of course, about a drip irrigation system for watering turfgrass? Drip irrigation system in turfgrass.
It has been done. I have done a number of research experiments on subsurface drip irrigation, and I'm assuming that's what you mean below the ground level, for agricultural crops like cotton and corn and soybeans and whatnot. It has been done in turf. I don't have direct experience with it. I know it's been done. There you would want to be very careful about filtering your water, especially if you took it from a pond or even groundwater and it wasn't from municipal supply. Usually if you get it from municipal supply, it's going to be expensive, of course, at least here in the United States, but it'll be clean. But when you go to drip, you definitely want to filter it. And then the next issue on subsurface drip is how close you space the laterals. And I think from what I recall in turf, you probably don't want to space the laterals much more than well, a foot would be 30 centimeters, 30 to 45 centimeters apart, because that way you assure you have a decent lateral distribution. Actually, it works quite well if you have a more impermeable layer below the drip line, because then it will actually spread above that more impervious layer if you have a layered system. But obviously they have to be, the laterals have to be spaced fairly closely to get a uniform distribution. I think it's done like in what we call double strips, or the parkways that are strips along sidewalks, because if you have a narrow strip, that's very amenable, or it's a good situation to use subsurface drip, because it's a narrow strip. So, and some of it depends on your geometry of your site.
Okay.
There's the chat. How efficient are water guns or giant long-range sprinklers as auxiliary irrigation in turf fields?
What we call big guns here in the United States are usually very uniform, and they can be spaced further apart. So instead of head-to-head coverage, you can go out to like 70% of the wetted diameter and still achieve quite good uniformity because of the pattern that they throw. They go out pretty well up to about 90%, and then they kind of tail off dramatically, but you can get away with a larger spacing between those guns, but they're very good options. And you can sometimes put them around the edge of a field and avoid the infrastructure in the middle of a field. So yeah, those are good options. They're used a lot here in North Carolina for wastewater systems, but they can have quite good uniformity and performance. You have to watch out about the drop size. If it gets too big and you have impact energy, you might have to, consider that, because they can get pretty big drop size with impact energy.